I've recently found myself wishing my dial indicators could store a reading for me. However, I don't seem to want to part with the couple $100 it'd cost me to get a digital indicator, so I decided to make myself something to do the job. Admittedly, it turned out a tad larger than its mechanical counterpart, but it's repeatable to better than 5 microns and only cost me $10, so it'll manage. The bulk of the sensor's size results from wanting the stiffness of the flexure low, while still printing with a coarse nozzle. I'm impatient. The purpose of the flexure is to guide the motion of this knife edge here in a repeatable linear path. I think taking a look at a simulation for this flexure may help show what I mean. In this load case, the load's applied directly along the axis of motion, aka the ideal desired load. And as you'd probably expect, the motion of the knife edge is the same as the motion of the contact face. There are no meaningful movements in either the other direction. But in reality, it's difficult or impossible to actually achieve that ideal with the sensor position just perfectly normal to the face that you're measuring. So let's take a look at an exaggerated but not impossible example where the force isn't on axis, but instead is at 45 degrees, like shown. Going back to the simulation and applying the same 45-degree load, we get a Z motion that still only shows 10 micron of error, but we also get a couple hundred microns of error in Y. Definitely more than I generally like to see, but I'd also hope I could usually do better than 45 degrees off axis I'm trying to get to. More reasonable, although I'd say still pretty conservative value, might be to say like 10% off. So let's look at what the error motion for being 10% off axis would be, and that just gives us 5 microns of error, which, it's okay by me. So, what are we doing with this linear motion of this knife edge here? Well, it sits inside the beam path of this little opto-interrupter. I love these little guys. For under $1, they can get you micron level measurements. Just splendid. They work like that annoying thing in the garage that won't let the door close when you unknowingly have moved the rake slightly. It's an infrared beam that comes out of the slit on one side, and if not interrupted, passes through the slit on the other side and onto a little phototransistor. Or to put it another way, gets light, current flows. No light, no flow. And, critically for using it as a sensor, little light, little flow. Since the current flow is proportional to the amount of light, the position of the knife edge within the opto can be output as an analog voltage, to be read by an Arduino or just a multimeter like I did for the calibration stuff I'll show in a bit. But first, let's take a look at putting it together. I want to have the signal from the opto available while getting in position, so the first thing I need to do was to make a driver circuit for the sensor. I'm not going to subject you or myself to hearing me try to explain electronics, but I'll link to an article below where I described how I put it together. And once the circuit was ready to go, I soldered some leads onto the opto, added heat shrink to avoid shorts and provide a little bit of strain relief. Plus, I just find it kind of satisfying to watch it shrink. I clamped the flexure into the pan device, threaded the wire through the opening in the body, and then I put a couple zip ties in these slots that I added for strain relief, but I left them loose, for now. I then just manually maneuvered the sensor until the meter showed about 4.5 volts. That put it about 10% below the max voltage. The further you get from the middle of the sensor's range, the less linear and generally well-behaved they are. So the 10% just keeps you a bit outside of that noisy area without sacrificing too much of the range. When I had it where I wanted it, I tacked one side with super glue and maintained pressure on the other until it cured. And then once that's set up, I repeated that with the other side and finally put a full bead of glue around the whole thing. After the glue was fully cured, all that was left is to tighten up the zip ties and glue on the stylus ball. I say stylus ball, I mean steel BB. I made this little calibration fixture that has a gap of a couple millimeters between this little shelf here and the stylus. And the plan is to put blocks of increasing and known thickness into this gap and record the resulting voltage value. Simple as that. The better you know the thickness, the less uncertainty on the resulting calibration. As a general rule, I like to aim for having my measurement tool be an order of magnitude better than what I'm trying to measure with, which means if I'm hoping to calibrate this thing to single-digit microns, I'd like to have something that's known to only hundreds of nanometers. Luckily, there are these wondrous, beautiful shiny bits of metal called gauge blocks. The set I have here are grade 0 gauge blocks, each of which has a thickness that's guaranteed to be within 150 nanometers of a given value. Michitoyo, you beautiful bastards. However, I should point out, if you're more responsible with your money than me, and don't want to splurge on exquisite shininess such as these, you can also do this calibration with feeler gauges or just blocks of metal that you've measured. Really anything of known thickness, preferably something that's reasonably stiff so it's not going to move around as you're measuring it. Ultimately, the best tools are the ones you got. Just keep in mind that your calibration can never be better than what you're calibrating with. As I've been rambling, you may notice I've stepped through the same sequence of measurements a good many times. I did that, along with a few more, to get a measure of the repeatability of this thing. With a total of 20 data sets and a bit of number crunching, I'd feel quite comfortable saying this thing's good to better than 5 microns over a range of about 700. This dynamic range, which is the range divided by the minimum measurement, isn't great compared to a good commercial competitor, but the performance per dollar is quite a bit better. But I think that's enough for today, so thanks for watching, and if you decide to build one of these for yourself, I'd love to hear the results. I'm really curious what the reproducibility is like on something like this.